By the way, I have edited the assignment. Okay. But by the way, I have, yeah. Okay, let me share. So I have uploaded an edited, an updated version of the assignment because there was one problem missing from there. Okay. So please review the updated. So Digante, I've already made you co-host, I think, so you could start sharing it.
Okay, yes, I'll start. Yeah, so okay. So if I remember correctly, we were discussing, I think we had stopped over here, right? We were discussing why some of the sort of justifications one can give to using DNNs as the parameterized models that we train, right? So does anyone have any questions or anything, or should I just move on to the next parts of this, or continue this from last time, let's say? Okay, so I'll just continue. Yeah, so if you remember last time, what we had said was that basically we have this some parameterized model which are these deep neural networks, and we want to somehow train and find out some values of these weights and biases so that our network behaves in a way that we want it to behave, right? And our desire for the behavior of the network we have expressed in terms of this loss functions, which in the sense again is basically this loss functions are again given by your data sets, right? So we have this loss function, and usually they come from some sort of sets of data that you have that you're trading on, right? So this is a situation. So in some sense, we have reduced the entire process of learning or the entire process of finding a good neural network, this training process, to optimizing a function, right? So if we remember our loss function, as we had said previously, is going to be some function that for say for negative loss likelihood, log likelihood, it looks like this, right? So it looks something like this. Or for something like mean square error, it might look like this. So you have some function and you want to optimize that. And as we had said last time, that this is actually a function of our parameters, right? So theta is going to be the set of all your weights and biases. These are the parameters that we want to, that whose value we want to find out, and that is the training process. So in some sense, we have reduced this entire problem of training to optimizing these loss functions over theta, right? So what we're solving now at this stage, we can think of that as an optimization problem. So how do we optimize this loss function, or how do we find the optimal value of theta which say minimizes this loss function? So there are various different, in general, there are many different optimization techniques and algorithms that one can use. But what we are going to look at is an algorithm that is actually fairly general in the sense that it works for a large class of various functions, and that is called this gradient descent algorithm. So gradient descent is in general an optimization algorithm. It can actually, it's not like necessarily that it only works for neural networks or anything like that. It can actually work for a large class of functions, and with certain restrictions, usually turns out that it works fairly well, right? So so yeah, as we said, that we have basically reduced this. So these 2 points basically are talking about how we have reduced everything to an optimization problem. So say let's talk about what kind of functions that gradient descent can optimize. So if your loss function is differentiable almost everywhere, let's actually, okay, so it's not just this, it has to, there are a few more things here. So of course the loss function needs to be continuous, and it needs to be continuously differentiable, if I recall correctly. In the worst case, I'm giving, yeah,
If it's differentiable, then it's continuous, right?
yeah, I mean, right. So this is not necessarily required, but yeah, it needs to be continuously differentiable. If I'm not messing this up, right? It's like
Yeah.
you can't
So
have
usually, what is required is that it should be set, and it can be like a non-differentiable on a measure zero set.
right, which is what I mean by
Yeah.
almost everywhere.
Yeah.
And when I
almost.
mean it, right, and then even when it's differentiable, it has to be different, like continuously differentiable on a set that is a complement of measure zero.
Yes.
Yeah. So this is accurate, right? So it continuously differentiable almost everywhere, I think. Yeah. So what this means is basically, so if for people who are not aware of measure zero sets and what that means, the idea is that you know, the best possible scenario is if it's differentiable and it's continuously differentiable. Continuously differentiable means that your derivative is continuous, should be continuous. If this happens everywhere, then you're good. But notice that we were using the ReLU function previously, right? So if you notice, ReLU itself is actually not differentiable everywhere, and the derivative is not continuous, right? So if you take the derivative of ReLU, it will look like a graph something like this. It will be 0 here, and then they'll have a jump over here, and then you'll have 1 over here, right? Okay, so if it's 1, it should be somewhere here according to the scale of this graph. But let's just say it's basically going to look like something like this. So this is not continuous. So if we if we say that we are only going to work with continuous functions or continuously differentiable functions, that's not enough. We also would like to accommodate for these jumps, but the only condition is that they must be in some sense in isolated points, or points or sets of points which have in some sense zero area, which is what we mean by almost everywhere. So this almost everywhere term basically refers to this sort of a situation where, say, you know, if you're talking about the real line, then there is just one point where it's not continuously differentiable, everywhere else it's fine. Or let's say if you're talking about a plane, then there should be a line, right? So a line is in some sense a zero area subset of the plane. So it's fine if some things are things on the line or along this line there is a jump. However, everywhere else it should be continuously differentiable. So what we are basically trying to get at is the probability of a randomly chosen point on your plane. If you choose something randomly, then the probability of that being the function being continuously differentiable at that point should be nearly, like, basically it should be 1. And what that will allow you to do is that even if you end up taking a derivative over here, or if you require the derivative over here, you'll just be able to shift it slightly and get an estimate for derivative, and that will be good enough in some sense. So that is what we mean by continuously differentiable almost everywhere. So, are there any questions? I think it will be a little bit more clear as to why we're asking this once we go into what the gradient descent is. And the best way to understand is, I think, just by looking at this particular picture. So if you think of your loss function as being this function in say on a 2D plane, and it has real values, right?
You know, which figure you referring to? There are two
This
figures
one.
here. Huh?
Yeah, this one.
Okay.
Yeah. So okay. So looking at this figure, let's say that we have a function from this this plane over here, right? The 2D plane given by this 2D plane, and this function is real valued. So this figure, in some sense, is a 3D plot of a function that goes from 2D to a single dimension real value thing. So what we want to do is we want to find the minimum of this function, right? And what you can do is you can start from any particular point, look at the gradient of this function. The gradient of this function is basically the direction in which the function increases the most. It is essentially the derivative of this function, but because it's a function that goes from R2 to the R, it will give you the direction in which this function is going to increase the most, right? So in this particular point, the gradient will be in this direction. Somewhere over here, the gradient will be in this direction, and so on. And what you do is you follow the gradient downward. So if the function is increasing the most in this direction, you move in the opposite direction, right? And then you take the gradient again. It's increasing in this direction. You again move in the opposite direction. And you take the gradient again, and you keep repeating that. So what that basically will lead to is that you'll basically in some sense follow the gradient, the slope of the function downwards, right? So you can keep doing this until you find or reach a point where you have a certain minimum, right? So this can be an optimization strategy, and this is basically the gist of the gradient descent algorithm. So one of the advantages of this is that this can actually work for very general functions. Like usually when you talk about more sophisticated or more specialized, let's say, optimization algorithms, things like say linear optimization, they work only on linear functions. You have various techniques that work only for certain class of polynomial functions. You have things for quadratic functions. You have things for even more general, let's say for convex functions. Gradient descent works for a really large class of functions, right? So that is a huge advantage. However, it comes with a lot of caveats. So the caveat mainly that we want to focus on, or the first biggest caveat, is that it is not guaranteed to find the global minimum. All it will guarantee you, and that is also a very weak guarantee we'll see, is that it will only give you a local minimum at best. So consider this figure now, the second figure that I have down here. So this one. As you can see, what's happening here is that if you just start from this point, okay. So yeah, if you start from this point, then you can start going down this slope. You'll follow this slope downwards, and then you'll reach this local minimum, right? And then you'll stop here, the way we have defined gradient descent. So what will happen is that you'll end up calling this your optimized position, and while there's a much better global optimum over here, which you'll end up not even looking at, right? So this is one of the problems that can happen. And in this particular figure, it happens if you start from both of these extreme positions. If you start here, it happens. If you start here, it also happens, right? So this is one of the problems with gradient descent in general, and this will translate you into situations where your model can get stuck into what it thinks is a good enough solution, but if it were to explore a little bit further, it would have found an even better solution to things, right? And there is no solution to this, at least if you use gradient descent, which is the one that we use. So this is one of the problems of gradient descent, that it leads to a local minima, and there's no guarantee for global optimizations. However, what turns out is that it still performs very good in practice. So there are two, I think, reasons for this. One is, well, okay, we're not really sure why it works very well in practice or how to even characterize that. But usually gradient descent suffices for training even against very complicated data sets, and we have complicated models. And one of the things is that, the chances of your loss function being specifically sneakily designed so that there is a global optimum somewhere, and that is the best, and everything else is like a much weaker local optimum, having this sort of a shape. It's a rather specific shape, right? So what are the chances of that you will end up having this particular thing? So that is one reason why, in some sense, you can think of this situation shown in this particular figure as being somewhat pathological. Although, again, nobody can really tell you that it won't happen. And if it does happen, you won't really know either, right? Because you won't be able to actually graph out your loss function. You don't know what your loss values are for various different sets of parameter values unless you've found them. And the other thing is that usually even if there are like multiple optimum points and so on, usually after a certain point, it's like when you train neural networks, you can get to a certain point where you know that you have gotten somewhere that is good enough. So your loss function may look like this, for example, right? But both these 2 points represent, say, 98% and 99% accuracy. Although, that is still, there is a lot of difference. Jump from 98% to 99% is not something trivial. But if you've reached 98% accuracy, maybe looking at your gradient descent algorithm for improvement is not the right place. Maybe you can use a different architecture of your DNN, maybe more layers, more neurons, more parameters, different layer sizes. That would probably have a more higher effect on the ultimate optimum that you reach than this. So I guess the reason it works well in practice is mostly that it turns out to be, and again, no one is exactly sure why this happens, but it turns out to be one of the many variables that will affect the quality of your training. This turns out to be one of the this situation turns out to be one of the less important ones in practice. So yeah, so now, right, so now basically we have this is basically an overview of the gradient descent algorithm. So any questions so far?
Now this peculiar graph that you have in here, okay?
Right.
Is that you were kind of trying to define differentiable, continuously differentiable almost everywhere. Is it continuously differentiable almost everywhere?
Yeah, both of these are. So for example, so both of these two pictures are in some sense continuously differentiable, because
the first one I can see, the second one, this one.
Right. So if we, the only point where there is any sort of break, I mean, I'm not even sure if this point is a break because this point is covering up the function in some sense. But even if this point is a break, it's just a single isolated point, right? So if we talk about, if we say choose any random point on the real line, then the probability of it being exactly this point, this exact one point, is going to be very small.
Yeah. So in that sense, ReLU, as per this definition, then ReLU would be also differentiable.
Yeah. Continuously differentiable almost everywhere, which is why
but the number, it is not that it has to be finitely characterized, okay? Or
right.
Like you said, it could be a plane, it could be a line, and things like that.
Right.
So it can be, but is there a requirement that has to be somehow characterized in some finitely representable form, or no?
No, it's the requirement specifically is basically this, that the probability in some sense.
The probability, the experience probability.
Right. So the this almost everywhere definition is in terms of probabilities and a generalized concept of area in some sense, right? So the probability of your if any random point, okay, I'm getting this error right away. Any random point is somewhere where it's not differentiable, right? It's not differentiable.
Is
this probability
is 0. Yeah.
So if this probability is 0, then gradient descent will work mostly. So if you think about this, what this is basically saying is that what gradient descent will do is it'll try to calculate or get the gradient at various points of a function. Right? So it's say you have a function that looks something like this. It's got a break somewhere. Okay, maybe I should. Yeah, maybe I should just create a new page and draw. Okay, I should probably just have a blank page instead of this. Right, so you say if your function looks something like this, you have something like this, and then here there is a break. Let's say that this point is a kink in some sense, and then you're going something like this, right? So say if you start doing a gradient descent from here, or actually even let's just so that I can explain better. Let's look at that. So let's say it goes up here, there's a break here, and then you have something like this. Right. So yeah, let's take this. So say you start doing gradient descent from over here. So here the downward direction of your gradient is going to be like this. So you move in this direction in some sense, and then you end up here. And now, the only situation where the fact that you don't have a derivative defined at this specific point matters is if you end up exactly at this point in the next step, right? But what are the chances of that happening? Like, it's much more likely that you'll end up slightly before it or slightly after it, in which both of which cases you're fine. You'll just follow this direction downwards and continue, right? So in that sense, if the probability of you ending up in these points where there are zero derivative, if that probability is zero, then you can say that the probability of a gradient descent algorithm halting because it can't find a derivative is zero. And of course, in practice, you can, sort of go around this issue by, when you're calculating the derivatives, you can just fix the value of the derivative at 0 for ReLU to be either 0 or 1, and that will basically simulate the situation. So when you're taking the derivative of ReLU, let's say, you can just say that the derivative of ReLU at 0 is going to be just 0. Sorry. So you can just declare the derivative of ReLU at 0 to be just 0. And if you do that, then you know that even if you end up exactly at 0, you still have a derivative value, and that behaves exactly the same as if you had just crossed 0, the probability of which is, more than, like, much more than you ending up exactly at 0. So that is the sort of the rationale behind this definition, or this requirement of this function for it to go. Yeah, understood. So another thing that we want to focus on over here is this idea that we're moving in the opposite direction of the gradient, right? There is actually a lot of number of heuristics involved in deciding how much we want to move. So such a step is called the training step, right? So each one of these steps that you take downwards following the gradient. So the size of this training step, you can actually fix it. So if you fix the size of a training step and you say that, okay, you're going to move, say if your gradient is some vector del nabla, then you move, say, some alpha times this, and then this can be your training rate. And one of the things that you can do is you can just fix this training rate and call it a hyperparameter. So hyperparameter is in some sense a parameter for your process that you're not optimizing. Like if the parameters are the things that the gradient descent algorithm is finding out, then the parameters of that algorithm has to be called something else. So we just call it hyperparameters. So yeah, you can fix this training rate to be just some fixed real number, and that is one way of doing it. Then it just becomes a hyperparameter. But there are much more sophisticated algorithms which actually vary this alpha, how much you move as a ratio to the gradient size. They vary it in various different ways, so that as you get closer and closer to the minima, you don't overshoot it, right? So that can be a problem. So you can again have a situation like this where, say, your graph is something like this, and say you're starting from here, and you realize that, okay, the gradient is strongly in this direction, so you just jump here directly, right? And then you keep jumping back and forth between these. So you can use, there are a number of heuristics that are used to reduce this and to mellow down this jump so that it happens gradually and approaches it like in a way that it makes this thing converge faster. So there are a number of such heuristics, and each one of them is in some sense a different flavor of the gradient descent algorithm. And you can go and look at the details of each one of these, and like each heuristic in some sense is a paper of its own. So you can go and read them, but usually all of those various flavors are just available as various gradient descent algorithms that you can use in whatever library you're going to use. So you can just pick one and use it. And as to how you pick one, it's so usually there is one called Adam that seems to work best in most cases. But you can also just try various different algorithms work out and see what's working best for your particular case. There is not much that you can do other than trial and error to sort of decide these things. Same for various hyperparameter values and such. So okay, so now any questions at this point before I move on to gradient calculation and such? Okay, I'll take the decision. So okay, so now let's see what we need to do, right? So if we can calculate the gradient at any point in our loss function, then we are done, right? Then we can apply gradient descent and go on. So now what we've basically reduced our problem to our algorithm to is to find the gradient at any point in our loss function. So remember that our loss function basically looks like this, right? So loss function is a function of theta. And let's say take the mean square error loss from last time. And that looks something like this, right? So we have the various correct outputs and we have the output coming from our neural network for the set of training inputs for a given value of theta. And you're taking the sum of those squares. So the mean of the squares. Okay, so since we're saying mean, which should be 1 by n outside over here, but yeah, so that normalization is always there. So this is your loss function in some sense. So if you want to calculate the derivative of this, that means we want to calculate the derivative of this entire quantity with respect to theta, right? So we want to calculate this thing. Right? Now you can use the linearity to put this derivative inside of this, and you can expand out this function, and what you'll get is essentially for MSC you will get something like 1 by n sigma I, then you'll have this difference, and then this entire thing would be times the derivative of this thing, so there will be del theta and xi comma theta, and this whole thing you're going to take a sum of this whole thing over, right? So essentially, it reduces down to an expression like this, and this is for mean square error. Similarly, for NLL or any other loss function that you'll take, you'll have some expression involving the output of your neural network, the correct output that you've chosen, or some other data points, and it will inevitably involve you taking the gradient of the output of the neural network with respect to the parameters. So what I'm trying to say essentially is that to calculate the gradient, in some sense you can always reduce it to calculating this particular value for a given x. And then calculating the gradient of your loss function would basically require you to somehow calculate these values for many different particular values of x, right? So what I'm trying to say is that we can reduce the calculation of the gradient to calculating this. So I hope this much is like no questions over here. Yes, no, say something.
Yeah, no doubts.
Okay. Right. So yeah, so now how do you calculate this thing, right? I mean, of course, calculating the gradients is not a particularly difficult problem, but remember that we need to do it several number of times, right? We need to do it, calculate the gradient of this entire loss function once for each training step, and you need many different training steps, and then you need to repeat this gradient calculation once for each data point, and you have like say tens of hundreds of thousands of data points. So this calculation is in some sense going to happen several number of times throughout your training process. So if you can optimize this in any way, that will be a really good idea, right? So a naive way to calculate your gradient could be that you just use your standard formulas for gradient and take every particular real value in theta and you calculate the gradient of that of the output with respect to that component of theta, right? So that was not going to be very optimal, and we'll see why. So let's take this for example, right? So firstly, let's forget for a moment that a neural network is this some complicated or some structure composed of layers and ReLUs and so on. Whatever it is a function that takes in some real numbers and outputs a single real number, right? So let's just think of the neural network for now as just being some function from real to real. And for any such function, you can, in some sense, write so r to the n, where n can be anything. So you can write this function as being, a composition of several fundamental functions, things like addition, multiplication, maybe even ReLU, or say things like cos or sine or so on. Right? Any r to the n to r function that you will be able to compute on your computer, because you need to do that, is going to be in some sense a composition of these things. So you can write down in what order you're composing those things as a directed acyclic graph. So for example, here what we're doing is we're taking cos x. This one is cos x, and then you have sine y, and then you're multiplying those two things together, and then you're adding that to your the division of sine y by y, right? So this entire function can be written as this sort of a graph-like structure. So let's just assume that we can write a neural network as this graph, and
one question: where does the cos and sine come? Okay, I thought that your neural network, at least the way defined.
Yeah, so it doesn't necessarily need.
But you have just thrown in cos and sine, but as per your definition of DNN, the way that we have introduced, they are all linear functions. No?
Right. So cos and sine won't come as one of your components of your DNN. Yeah. But okay. So what can come is this some.
But it can't, right? You can actually add any sort of functions you want. So exactly. The ReLU function is actually not linear. It has a bit of a non-linearity, as in it's like
instead of using ReLU, you could add something else. Okay, and that may involve tan, cos, and those kinds.
Yes.
Okay.
Yeah. In fact, certain things like tan H are kind of quite common, right?
Yeah, I got it. Yes.
Yeah. So I've just put this here just as some example. Yeah.
Yes, I do understand, but it can happen. Okay, like he pointed out.
It can definitely happen. I mean, there's nothing that is stopping you from doing this. Is basically. So okay. So in any case, let's say that this is sort of the function whose gradient you want to calculate. So you want to calculate calculating the gradient is basically calculating the derivative of the output with respect to x and y. So if you do this, in a standard way where you calculate the derivative with respect to x first, and then you calculate the derivative to y, what you'll end up seeing is that you're doing a number of those calculations many different times, right? So if you calculate the derivative with respect to x, what you need to do is you need to sort of calculate the derivative of this function with respect to x. So for that, you need to calculate the derivative of this with respect to x and this with respect to x. And then, okay, so this is, I think, x by y. I misinterpreted this. This is x, right? And then again, you need to calculate the derivative of this with respect to x for that. And for this, again, you need to calculate the derivative of this with respect to x. And again, to calculate the derivative of this with respect to x, you need to calculate the derivative of. So, okay, so here directly, again, you just go here, right? So if you follow along these calculations, in some sense, you're going down the graph all the way to x. And then while you're going back up, you're just calculating each one of the piecewise gradients and multiplying them, right? So the gradient of this entire thing with respect to x, it's going to firstly split along this thing. So you reduce it to calculating this, and that reduces to calculating this, and that reduces to calculating this. And then from here, when you go back up, all you're doing is essentially multiplying the gradient of this with respect to x, which is 1, and this function with respect to this particular input, right? Because of the chain rule. So in general, whenever you have a node and you have some input and some output, and you want to calculate the gradient of this output with respect to x, let's say, and this node has, say, some function f over here, then what you want to calculate is this. And if this value is, say, w1 okay, let's just call it w. What you can write this as basically is del f del w, and this you'll know from, since each one of these functions derivatives in some sense, this component functions, and this del f del w times it's going to be del w del x, right? So if you do this in your standard way, where you pick each component of theta, which in this case is x and y, and you decide to calculate the gradient of these, what you end up doing is you implicitly end up calculating these values many different times, right? So for example, for this one, what happens is that you end up calculating this particular, so W7 is, say, our final output, right? And this one, let's say this one is called a W5, I think, according to this, right? So if you when you are calculating the gradient of your output with respect to x, you'll go down this path, and then you'll end up calculating del W5, sorry. Del W5, and this one is W3, right? So you'll end up calculating del W5, del W3. Also, when you go down this path, you'll end up, so also when you want to calculate the derivative with respect to y, you'll end up calculating del W5, del W4, and then again you'll end up calculating, so okay, this derivative is actually not shared, but
del W7 by del W5, right?
Right, that one would be shared. So I wanted to show something that was at least one level deep, but I think this example is bad for that. So at least if you look at del W7, this particular value you'll end up calculating twice implicitly, right? So when you calculate del W7, del Wx, sorry, del x, you'll end up calculating this value because you want to go down this path. When you calculate the same thing for y, you'll again have to go down this path, and you also end up calculating this value. Similarly, del W7, del W6 will be calculated multiple times if you do this once for every component of theta. And here we have just two components, right? And this graph is also in some sense slightly sparse. So if you have something as interconnected and dense as a neural network, and if you are calculating it for all your parameters, which may easily be in the millions, then you realize that this is a lot of repeated calculation that you're doing. So there's a huge scope for optimization over here. And that is where this autograd algorithm comes in. So what autograd basically does is that it will basically do all of these shared calculations only once. So you start from the bottom. Instead of going from the output side back to the input side, you start from the input side and go to the output side, and you firstly calculate all of the values of all of your intermediate functions, right? So for some, let's choose some value of x and y, and for that we can end up calculating all of the values of an intermediate function. So let's say if we choose x to be, okay, let's say that we'll have x equal to 90 degree and y equal to 180 degree, let's say, right? So then this one intermediate value is 90, and cos of 90 is going to be, right? I may not make, yeah, no. And this one is going to be 180. Sine of that is going to again be 0, and then 0 times 0 is 0, and then 0 times 0 is going to be 0. So that's fine. And then you'll have 180 coming in over here. Sorry, this one actually. You'll have 90 coming over here and 180 coming over here, and this one is going to be 180 by 90, or actually 90 by 180 if I'm not wrong. Yeah, and then that would be half. So half is going up over here. And then over here, you finally have 0 plus half, that is half. So you calculate all your values. And then you go back calculating all of the derivatives of each one of the node functions with respect to each one of its out inputs, right? So for add, you calculate the derivative of add with respect to your input for this given values of for this given intermediate value. So if you look at just this part of the graph in isolation, let's say, right? Then here all you have is you have a function add, you have two inputs, which is half and 0, and you have an output half. And you can calculate the derivative of this function add with respect to each one of its inputs. So we calculate that and mark our edges with that. So the calculating is, so if you calculate the derivative of add with respect to the first input for these two given particular given values, it's going to be just be 0, right? So yeah, so it's going to just be your this particular no, it's going to be, sorry. Yeah, that was stupid. So it's going to be 1, right? So because you have x plus y, and what all that you're doing is you're doing this. So for add, the derivative of all of these of your final output with respect to each one of these intermediate inputs is going to be 1. So we label the edges with that, and then we go back down the graph again. We look at mult similarly, and for mult again, the derivative of each with respect to each input of this is going to be the value of the other input, right? In which case, both of these are, or in this case, both of those are 0. So both of these is going to be 0. And then finally, you have cost. So the derivative of cost with respect to this input is going to be sine of that input. So that in this particular case is going to be or minus of sine, which in this particular case is going to be -1. And derivative of sine is going to be cos, and cos 180 degrees again -1, right? I hope I'm not making like saying entirely wrong values over here. Someone do correct me if I'm saying something entirely wrong in terms of these values.
Okay.
Similarly, you can, yeah.
Okay. Yeah.
So okay, so similarly for these for the division, you can come up with some values over here. Now the point is that then if you want to calculate the derivative with respect to x, all that you need to do is you need to find out all the paths from your input to this particular variable x and multiply along each one of these paths and add them together. This comes by simply expanding the chain rule, right? So if you expand the chain rule, what that basically is going to give you is that the ultimate derivative with respect to x is going to be come from two contributions coming from the two inputs of your final add function over here. And for each one of them, again, it's going to be two contributions coming from those two inputs. Now, some of these contributions have 0, right? Because they don't ever reach x. So in some sense, if you don't reach your input x, if you reach some other input, then the derivative with respect to x is going to be 0. So those entire paths that don't reach x is going to contribute 0. But each one of these other paths is going to contribute something. And what it's going to contribute is going to just be the product of each one of these partial derivatives, right?
Diganta, you just now made a mention of chain rule. Okay.
Right.
Have you shown that? What exactly the chain rule is?
Right, sure. So let's take this particular function and work it out specifically, let's say. So what we have over here is again cos x sine times sine y plus x by y, right? So what we want to calculate says this. So then according to chain rule, what chain rule allows you to do is basically allows you to, this is the chain rule essentially. F of g of x is just del f del g of x times del g of x del x. So here I'm this is in some sense abuse of notation. By g of x here, I mean the intermediate value that you're passing to f, right? So it allows you to express your derivative as a product of the two derivatives, where the first term of your product is going to be the derivative of your outer function or the last applied function with respect to its intermediate input. And then the second term is going to be the derivative of the intermediate input with respect to your original input. So if we take this example over here, for if you had the DAG for that, it would look like f g and then x, right? And then this is going to be del f del g of x, right? And this is going to be del g of x del x. So as you can see, basically the derivative of this entire function is going to be just the product of these two derivatives. And this is what the chain rule says. Similarly, if you have, so we'll come to this specific calculation in a second as an example, but let's just look at this other situation. Say you have something like this, del x of f of u of x and v of x, right? So you can, firstly, you can forget that u and v's are, as a first step, you can forget that u and v's are functions themselves and just call this f of u comma v, right? So you will see that if you try to calculate this derivative, what this will come out to be is del f del u times del u del x plus del f del v times del v del x. Now, this is basically just directly from the definition of how derivative works in some sense. So if you look at the derivative of this function is something that takes two inputs and gives you one output, right? So the derivative of this function is going to be some vector along which this function increases the most. So the derivative of this function is going to be this particular vector, right? Del f del u, del f del v. And then you have these two intermediate functions, and so you don't want the derivative of this function, you want the gradient of it with respect to x, or the partial derivative with respect to x. So you want to ask that, okay, if I know that, okay, if I move u this much, then this function changes by this much. If I move v this much, this function changes by this much. But if I were to move x by some amount, how would this function change? So to know that, if you move x by some amount, then you have to know how much u changes. So that is del u del x. And then f would change proportional to that according to how much f would change if you were to change u a little bit. So this becomes this. And then similarly, you'll have del f del v times del v del x. So in general, basically, you can, if you have any function that looks like, or if you have a composition of two functions that looks like f of u v w and so on, and each one of these again can have as like whatever arguments as they want, then in general the derivative of this with respect to any particular variable is going to be del f del u times del u del x plus del f del v times del v del x and so on. So this is the chain rule. And so okay, is this clear? If not, I mean, just look up the chain rule and look at the, like, you can also look at the derivation of the chain rule and so on. I think it will be clear. Del w del x del f del w. So in this situation, if you have, say, in terms of your DAG, if you have f and you have your u v w, then what all that we're saying is that if you want to calculate the derivative of your f with respect to x, then that is going to be derivative of f with respect to u. So that is going to be whatever the gradient label that you have on this one. So that is this. Oh, sorry, not that. That is going to be this. And similarly, you're going to have a gradient level here, and that is going to be this, and you have a gradient level here, and that is going to be this. And then these ones you can again recursively expand using chain rule, and these will again expand similarly as sums of products of your the gradient labels on each one of the edges over here. And if you expand all of these out, what you'd get is this fact that I'm stating, where you'll end up looking at the product of all the values along each path coming from your input, and then you'll have to take the sum of that. So as an illustration, I guess what we can do is we can look at why that happens in this particular case. So in this particular case, if we try to calculate the derivative of x with respect to x, let's say, so del x of sine x cos x, of course.
Which path are you doing it on?
I'm doing it on this entire thing. So I'm going to calculate the del x of this entire
But
thing.
you do that by enumerating each path, huh?
Yeah. So I'm going to do that firstly by your normal by hand as you would calculate a derivative, and then show that how that ends up becoming equivalent to enumerating the paths. Okay. As an example. So cos x times sine y plus, this was x by y. So this entire thing is going to be del x cos x times sine y plus del x by y, right? So now this is basically saying that, okay, it's the, so remember that this is 1 times this plus 1 times this, right? And this 1 is coming from, in some sense, if you were to look at plus as a function, this 1 is basically the derivative of that function with respect to its first input and with respect to its second input, right? So that's what these two ones were over here. And so what we have done it in some sense is we have already gone along 2 paths down over here, and we have multiplied the ones that we had labeled these 2 edges with. And now what we're saying is that now we need to calculate the derivative of, or the gradient of this, which is going to be the gradient over here. And similarly, this derivative, which is going to be the gradient over here. So let's recursively expand each one of these things again. So this one becomes, this one is going to become, so derivative of cos is going to be minus of sine. So del x of cos x is going to be minus sine x. Then you have an implicit del x, which is going to simplify to 1. Okay, so instead of doing that, let's do it step by step, right? So the outermost function here is going to be your multiplication. So del x of this one times this one is going to be cos x times del sine y del x plus del cos x del x times sine y. So this comes from the product rule, but you can in some sense say that this is the definition of, or these are the gradients of your multiplication function, and what you're doing is essentially expanding out in terms of the chain rule as well. So that is another way you can look at it, even if what you're doing is taking the multiplication. So this again is with respect to taking these 2 paths, right? So this cos x is basically the value that we had labeled over here, right? So in our case, it was 0, but essentially we have some cos x label over here, and we're going down this path. And then we are saying that we're going to recursively expand out this over here. Okay, so I think I misspoke. So so, and similarly, sine y is going to be the derivative that is going to be, so okay, I think I misspoke over this. So cos x is going to be the label over here, right? And this is represents going down this particular path, and then we are saying we're going to recursively enumerate this one over here. Similarly, sine y is going to be the derivative that we label over here, and this represents going down this path. And what we're saying is we're going to enumerate or recursively expand out this over here. So if we do these expansions recursively, sine x del x becomes again, so you have your cos x from previously times, so del sine y del x. So we can call that as del sine y del y, which simplifies to cos y. And then you have del y del x, right? So that again corresponds to going down this path. So this is the label that is on this edge. So now notice what has happened. We have actually gone down this path and we have multiplied everything. So it 1 times, that was the label here, times cos x, that was the label here, times cos y, that was the label here. And now what we have at the end is del y del x. So del y del x is 0. So this path's contribution in some sense becomes 0. But let's look at this other situation over here. So here again we have 1 times we had gone down this path, which gave us sine y, times we had del cos x del x, right? So that is again going to be minus of sine x del x, right? So here again we are going over here. So minus sine x is going to be the label of this one, and del x is going to be 1. So what we end up is getting is we are going to end up getting the product of all of the edge values along these path times 1, because we are ending up at x, right? So this is what we get when you recursively enumerate the left side of this of this equation. Similarly, if you enumerate this side, what you'll get is each one of the paths over here. So let's just take one path, for example. And I hope that will be enough to sort of show you what I mean. So we have already gotten 1 over here. We have already come down here, and now we're expanding out this one. And so del x of y by x is going to be, it's going to be 1 by y square. So it's going to be x by y square del y del x. So x by y square is the edge along, like the label along this edge. So this represents going down this path, and then we have del y del x over here. Similarly, you have this plus 1 was coming from here times y by y square del x, right? So this represents going down this edge, and then our path is going to be this one, right? So we're multiplying 1 over here, and the label over here is going to be y by y square. Because again, if you have w1 by w2, then remember that this one was w1, so the derivative of this with respect to w1 is going to be this level. So again, this one becomes 0, this one remains 1, and what we end up adding to our final derivative is the product along this path that leads us to x of all the edge levels along this path. So that's why ultimately it's going to be the product along, like you take each path from your output to each input, and you take the products along that path, add them up, and that is going to give you the derivative with respect to that input, right? So now once you have the forward values along all of your functions. Okay, so any questions up until this point? Yes, no. I hope that I'm like most of these things are clear.
Yeah, no questions.
Yeah. So okay, so once you have all of your the intermediate values calculated, which were in this version of the slide, it's the black values that I've written over here for a particular input, let's say. So once you have all of your intermediate values calculated, then what you can do is you can keep going backwards along your graph you can either take, any sort of backward search.
Yeah, see, what
will
is
do.
not clear here is, I mean, you motivated the whole thing saying, okay, you shouldn't be doing repeatedly. Okay. Now, what is done once, what is done for each, data point is what is not clear. Okay. So
what is the repetition that we're eliminating?
you started motivating the whole thing by saying you don't want to do some repeated calculations. Okay.
Right.
What got lost in this whole thing was how you are avoiding that. Okay. So in all these details that you presented, I don't know. I mean, you have to also ask the question. So I felt like for each data point you want to know I mean, obviously the output of your optimization process is the optimal value for your theta, correct?
Yeah. So that is, yeah.
Yeah, but that so how, given the graph, you do some computation once for each of the path and then you instantiate that. So you pre-compute certain things. That's what you call as labels. And then you reuse them for each data point. Is that what is happening here?
So
No,
one
we're
way
not.
to think of it is like, suppose you have X, right? So at every node of this, like in add, mult, cos and sine, you calculate the gradients with respect to each of these variables, and then essentially you back propagate it. From back propagation meaning is that you use the thing which you calculated at mult. Okay, you use the gradient which you calculated at mult and you back propagate it to cos, and you back propagate it to sine. Okay, because essentially when you are calculating it with respect to x, it will be something like d of cos x by dx, and then like d of mult of xy by d of cos x.
Yeah, but then okay. So the point I'm making is, this is the point that I want explanation from. How are you avoiding the repeated calculation?
So we're not avoiding derivatives. You're gone.
So you said some autograde eliminates this repeated computation.
Yeah. So specifically, what it eliminates is this thing right here. So for example, if you look at the partial derivative of this output with respect to this intermediate value, then if you were calculating just one gradient or the derivative with respect to one of your input functions at each point, you would end up calculating this particular gradient twice, or this particular partial derivative twice. Because if you want to calculate the gradient of W7, let's say, with respect to X, then you need this, because in this expression W7 by del X, if you expand this out, you'll get to see del W7 by del W5. Right? Similarly, if you calculate del W7 by del Y, so here remember that our theta is basically just X comma Y. So here also you'll get to see this one. So instead of calculating this first and then this again, and which ends up calculating this one twice, what this autograd backpropagation will allow us to do is that it will just allow us to go back along the graph, accumulate all of these values, and then whenever we reach a particular input, we'll just multiply all of them and add it to the gradient for that particular input. So that basically allows us to, in some sense, avoid calculating these values multiple number of times. So if you were doing it directly, you would have to calculate this particular value twice. But here what we do is we go down along this. So that calculates del W7 by del W5. We go down along this. Similarly, that calculates del W7 by...
but that's what you mean by you storing that as labels.
Yeah, as labels along the edges. Right? So then then you go down along this and this, and you calculate all of these values, but you do them exactly once.
Yeah,
And
so
now,
because you've stored them as labels, the next
Hmm.
time you come along the path, you already have it. Okay.
right, exactly. And whenever you reach an x, then what you do is you have traced some paths to reach that x. You just multiply all of the labels along that and add that as a contribution to del output del x. Similarly, if we reach y, we'll just we'll multiply all of the labels along that path and add it as a contribution to del output del y.
Yeah.
So this avoids calculating this particular derivative many different number of times. So in that sense, it reduces some calculation that you have to do. And
But
this
you
is,
have to repeat all these things for each data points, though.
yeah, that we'll have to do anyway.
Yeah.
So there are some optimization with respect to that as well in some approximation. Let's say that.
I mean, okay, that was my kind of explanation thing. I mean, I don't know if other people appreciated that point or not.
Yeah. So are there any questions? I think I'll just. I mean, I think we are somewhat running late, right? But if possible,
okay, so I think
if possible, if people do have some time, I just want to take 2 minutes or 2-3 minutes to talk about.
I think we have. Okay, the hard stop should be at 5. Okay.
Is that okay with everyone?
Yeah.
Yeah,
Hard
that's
stop
fine.
at 5. Yeah, which is 7 minutes. Yeah.
Okay, yeah, 7 minutes should be enough to talk about SGD. So, yeah, so before that, any questions or anything at this point that you want me to? Okay, I'll just continue with SGD then. If you do have questions, just stop me. So yeah, as such, say that this particular autograd backpropagation optimization, this only helps you calculate this one particular value. So this is an optimization that is for calculating this thing, del n del x comma theta, right? So if you go back to this particular slide that we had basically, if you remember, we wanted to calculate this entire derivative. So this is your loss function. This entire thing is L theta. This entire thing. And you wanted to calculate the derivative of that, which we reduced to calculating the derivative of this. But remember that in this reduction, we had to sort of, do this calculation for each data point, right? So our final expression, in some sense, that we want to that we end up calculating is going to have a sum over I, right? So we're taking a sum over I. Here we have xi comma theta, and we're having to do this calculation for all the i's that we have. So in a typical data set, you'll have at least tens of thousands of data points, right? So what you end up having to do is you end up having to do this gradient calculation for all of those tens of thousands of data points if you want to calculate the loss of this, the gradient of the loss function, right? So as you can imagine, that would be still be very difficult, right? This gradient calculation, although AutoGrad optimizes it quite a bit, you can imagine that theta will have millions of parameters, and it is still going down a graph with potentially millions of nodes. So you still want to do it as few number of times as you can get away with it. So that is where stochastic gradient descent comes in, where you sort of try to reduce the number of times you have to do this calculation. So
the number of times for the points, the number of points.
Yeah, the number of points that you have, right? So AutoGrad reduces the time spent doing one of these calculations, and then SGD is going to reduce the number of times you do this calculation. So the full loss function is going to be, so let's say that you have n data points, or capital N. So here I is going to go from, let's say, 1 to capital N, and then you have something here, right? So what stochastic gradient, so then, if you do this, you'll have something here. Sorry. So you'll have something here, dot, and then del theta of n, right? So it'll look like this essentially. So what stochastic gradient descent says is that instead of doing this calculation for this entire huge sum, instead take a small part of this sum. So fix a mini batch size. So yeah, so split it into a number of different mini batches. So let's call the mini batch, let's say the size of each mini batch is small n. And then instead of calculating the entire derivative here, you calculate this gradient. You calculate, sorry, not L. You calculate the gradients going from I from 1 to small n of this. Right? For your first step. And then for the second step, you go from n plus 1 to 2n. For the third step, you go from 2n plus 1 to 3n, and so on. So if you imagine your entire data set is this huge array, instead of every time you going over a sum over of this huge array for each training step, that is for each time you go down your gradient, instead you split your array into multiple different mini batches, and then you calculate the gradient with respect to these points, take a step down your graph, right? So and then you calculate the derivative with respect to these points, take a step down your graph, and so on. So this is called the stochastic gradient descent algorithm. So the important thing here is that the reason why this works, or we expect this to work, is that since your data sets in some sense comes from this whole large random distribution, taking the gradient over a smaller thing produces an estimate of the true gradient, and I mean estimate in the probability sense. In the sense that if you were to take many different such mini batches and average the gradient out, you would actually get a very good, something very close to the actual gradient of your loss function. So in some sense, at each training step, you don't use your actual gradient, but you use a close enough approximation of it, an estimate of it. So this SGD replaces your actual gradient with an estimate of this gradient, and you can expect this to behave identical to your to using the entire sum, and you're getting your actual gradient under expectation. So under expectation in terms of probability. So if you take average over multiple runs,
Yeah, how do you split your original data into these batches?
Right. So you fix some mini batch size, which is going to be another one of the parameters that you the knobs.
That's right. But then what data points?
Right. You do it randomly.
Those batches is random. Okay?
Yeah, it is random, and it is done. So once you have taken, say if you have k different mini batches, once you've gone. So once you've done one step for this one step for this one, and gone all the way to the end, then you don't use the same split again. You shuffle your entire data set, and then you do another random split. That is just so that you don't end up gathering some correlation which does not exist in your data, right? So if your splits was, because you're doing random splits, if your particular splits happen to be something that was that exhibited some wrong correlation and that produced bad estimates of your actual gradient, then at least after you've trained over all your batches and you go back and you shuffle again, then things are random again and you'll get better estimates and so on. So you keep doing these splits every time you reach the end. And this entire going over this entire set of data once is called an epoch. So epoch, and at the end of each epoch you redo your splits randomly.
Yeah, but so you shuffle and then you go again, huh?
Yeah, you shuffle and then you do this entire epoch again. Yeah.
Okay, I think it's good to stop at this point, unless you think. But I think what you, I mean, if you have any questions about these things, and I think, please go ahead. And then I have a point, to make about, what the topic for next class, and then and so on. So what remains to be done. Yeah. This is about the nuts and bolts of gradient descent, correct? Yeah, that you wish to cover. Any questions there? Hello?
Yeah, no questions from me.
Yeah.
No.
Now, what I want, for you, not now, okay, I'm hoping that you will do is, when they actually do the training, how much of the nuts and bolts that they need to understand in order to use it while doing the training via back propagation. Okay.
Right.
Thing.
So I'll do a
That,
demo.
even if you don't want to mention that, I mean, that is something that I'm hoping that you will cover. Now, for example, deciding the number of batches. Okay?
Right.
And but the other one of your graph, how those things, the autograd optimization, that I guess one that doesn't need to worry about. That is automatically handled, correct?
Yeah, so the autograd is mostly automatically handled.
Are there any parameters there that a user who's using the tool to train need to be aware of?
No.
That he has control over. Okay.
No, so the autograd thing, there are nothing like, yeah, but the only thing that you need to keep track of with respect to autograd is that you just there are certain times when you want to turn off this autograd calculation when you're not training, for example, and that is, other than that, there is nothing else that you need to worry about. So I ended up going in more detail while speaking than I wanted to go initially, but yeah, you don't need to worry about the details of the autograd function.
And also the loss function that you use is fixed in most tools. You don't have any choice in.
No. There is actually a number of different loss functions that one can choose. So
is that something that that you make a choice of?
Yeah, and that depends on the kind of training that you want to do. In fact, this is why I covered this broad sense of classification works, in the sense that if you're doing things with say, if you want to do things that look like regression, then you would want to use something like a mean square error loss or some other loss based on distance. If you're doing classification, then you want to do a negative log likelihood loss. There are other loss functions and things.
So we are okay. So what is the okay? Just as a peek to the next class, I presume that we
I would
need one more class for sure, where you will
Yes.
actually see the actual code and then have them illustrate how they could pick on whatever parameters that they have choice over, and then actually how to run it. Okay, that would be the topic next.
Yeah.
Right?
I think yes. So I think then for the next class, I'll take some object recognition or MNIST, that sort of a data set, and show how to do that in.
Yeah. So yes. So you guys, there'll still be one more class where you will really see how.
Sir,
yes.
I mean, in terms of scheduling, if that is like maybe I'll take less than one class.
No. What was your point? If okay, because we had planned for two. If having
So in that sense, if that is an issue, we can not take one time.
We will adjust that. Okay, even if
Okay,
it means
sure.
that we'll have to have an extra class to fit in all the things. We already have some leeway. Okay, in terms of the things. So I don't think you need to worry about that. Yeah.
Okay.
So you could do that on Wednesday, and so for the rest of you guys, I mean, what I'm saying is that if you review the lecture, and then if you have any questions, make a note of it, and you still have questions that you can ask about either the theoretical thing, which Diganta just sketched over, or more importantly, in the way that you use it for doing actual training, which is something that you will need to understand and learn, as for your project as well. Yeah. Okay. So that you will have time to ask questions in the next class. Okay. So what is